Hello. The topic of our research is segmenting glandular biopsy images using the separate merged object algorithm. David Sabban and Professor Ilan Shimshoni from University of Haifa conducted the research. The analysis of structure of histology images is crucial in determining whether biopsy tissue is benign or malignant. One weakness of the semantic segmentation method, namely mistakenly merged closed objects. If two or more objects have been merged, interpretation of the biopsy can be erroneous, false positive. As we can see in the figure, this algorithm aims to separate the objects that have been merged in a biopsy by drawing a line along the points where they touch. We determine whether a line should be passed along the edges to separate the object according to a loss function that we define. There are two preconditions to our algorithm. The first, the output of the segmentation should be a semantic segmentation of a biopsy image. The second, in the object that we are analyzing, at least one of the components is close to the object contour. In a colon biopsy crypt object consists of 6 components, with the nuclei located near the contour. This requirement is satisfied in many glandular tissues, as, for example, breast, thyroid, and prostate. There are 3 main parts to the methodology. In our algorithm, the line plays a significant role. A line can be represented in several ways. In our algorithm, lines are presented as location on the image border, location 1 and location 2. The second factor is the loss function. In the first part of the loss function, we want to separate when we are at the border of the object. Example given at the nuclear region. For each potential line, pixel value of the semantic segmentation are calculated for the object itself and for the component, for example the crypt and the nuclei. Our second objective is to determine whether an object is likely to be an object based on its distance from the contour, probability based on a condition. By given distance, what is the chance to be a component? From the Cannon density estimation figure, we can see that the nuclei is centered in the border, whereas the rest is not. The last part is to find the perfect position of the line in the image. We calculated the loss function value for each potential line after scanning the image space with horizontal and vertical lines. Then, F-min optimization is applied. Our method was applied to 402 crypt objects from 7 different biopsy images. 3 images are of malignant tissue containing 81 crypt objects, and 4 images are from benign tissue containing 324 crypt objects. The proposed algorithm method improved the intersection of reunion score by 10%. This improvement was noted in both cases for malignant and benign biopsy. Thank you for listening.